All right. So this thing is on. For those watching the webcast, I just did 5 minutes of lecture, introducing myself, handing out things. You haven't missed much. The way the webcast works is basically they are recording everything that I'm saying off of this microphone, and I have to turn this microphone on every time I lecture to do it. They are also recording exactly what goes on this screen here. Okay, so obviously there's no one videotaping me, so you can't see me. But you'll be able to, after class, go to this website right here. Okay, and this is going to be something I'll distribute. I'll tell you that in about a minute. But you can go to this website right here, and all of the lectures will be on the web, and you'll be able to access what I write, what I say, which I think makes it a little bit easier for you in case you have to miss a lecture or if you have to see a lecture again. It's also used heavily by people outside of Berkeley. So it's interesting. I get a lot of emails whenever I do this of people asking questions from India or, someplace in Asia or so. So that's kind of a nice thing to do for the rest of the world. But one thing that you have to be careful about with this webcast is that sometimes because of the webcast, you're not forced to come to lecture. And I recommend that you come to lecture. Because what happens with the webcast is, at the end of the semester, you got a lot of projects and that sort that you're doing. You start saying, well, all right, I got to finish this project, so I'm not going to show up to lecture. I'll watch the webcast later. And the majority of people who do that do not end up watching the webcast, and then you're in trouble. Okay, so I guess if I detect that happening, I'm going to stop the webcast, because I've seen it happen in previous courses. But it's certainly going to keep going now. And those listening on the webcast, don't worry too much. I've never stopped it before. Listening on the webcast means that there's someone listening right now to what I'm saying. Okay, so I guess I have a few things there, but let's go straight to the course information sheet. And let's do this version. Okay, so you all have this right now. You have all the relevant information about the staff for teaching the course. So this is me. You've got my email, my phone number. My office hours are going to be Mondays 2 to 3 p.m. and Thursdays 3 to 4 p.m. in my office, which is 574 Corey, which is kind of a difficult office to find in Corey Hall. So how do I best tell you how to get there? Actually, I can draw how to get there right here. So during these lectures, the way that I do my lectures is obviously I'm using a tablet PC here. So I'm going to be able to draw and write everything that I talk about, well, almost everything that I talk about. So this is kind of a substitute for using a chalkboard, and maybe it's a bit better because you'll see not only can they capture this on the webcast, and you can watch the webcast later on, but I will also put all of the notes and all the materials, including the materials that we handed out to you today, out on the website for this class. And the website for this class is not the Bearfax site. Is it called Bearfax? It's not called BSpace. Yeah, it's not the BSpace because I don't like BSpace that much, so I don't really use it. Right? What I'm using is an actual website for the course on the EE instructional site. I think it ends up being better because it's easier to look at and that sort of thing. I think it stays up more as well, so it doesn't go down as much as maybe BSpace might. So to get to the website for this course, just Google actually. Type in Google EE140, and you'll probably go straight to this course here. And if you go to spring 2009 or so, then just update that to 2011. 2009 was the last time I taught this course, okay? And that'll give you all the latest on this. The website is not up yet. It should be up either by the end of the day today or tomorrow sometime, okay? But there's my information there. Now your teaching assistants, well, I was going to show you where my office is. Okay, so this is Corey Hall. Okay, this is Hearst. Okay, my office is on the 5th floor. If the elevators are here, my office is right there. Okay? The reason why I'm telling you this is because it seems to not make sense because you can go all around a 5th floor Corey Hall and never find my office because you think the numbering scheme is not right. But actually the numbering scheme makes a lot of sense. Go to 5th floor. This office right here, I believe is 501. Okay, and then it goes all the way across here, increasing in numbers, till it gets to here. which is the largest number on Corey Hall, which is 574. So it does make sense, but anyone looking for my office always gets lost for at least 10 minutes and has to ask someone eventually where it is. Okay, so here, you know where I am now. I'm right here. Okay, that's where you want to go if you want to see me in office hours. And these are my times right here. So the teaching assistants, Travis, his office is right here. His research office is right here. You have his telephone number, email address too. But the office hours for your TAs will not be held in their offices. They'll be held in the center of the Corey Hall courtyard. So the Moore room, I guess you have a ping pong table there or something like that. Is that right? Yeah, so that's where the office hours will be held for this class. Travis will have office hours Mondays 11 to 12 a.m., Tuesdays 9:30 to 10:30 a.m. And there's a reason why his office hours are bunched up in the beginning of the week. That has a lot to do with when your homework is due. They will be due Tuesdays at 5 p.m. Okay? And we'll try not to deviate from that. We were able to not deviate from that in spring 2009. I think we can do it again. But we're pretty much going to have a steadfast homework assignment. You'll get approximately once per week homework assignment, which will keep you busy pretty much every week of this class. Yang Lin's office is 373 Corey Hall. You see his telephone number there. This is his email address. His office hours will be Tuesday 2 to 3 p.m., so another Tuesday one, but also Friday 2 to 3 p.m., also in the Moore room in Corey Hall. Okay, so at this point, now that you know when the office hours are, I'd like to ask if there's anyone who cannot make at least one of these office hours, in which case we'll try to make a change to accommodate. Is there anyone who can't make at least one of these? Okay. There could be someone that's afraid to speak up too, so if you are, just send me an email, let me know that you want to see an office hour change, and we'll try to accommodate that. Okay, but at this point, I don't see any need for an office hour change. So the lecture, you know, Tuesday, Thursday, right here, 213 Wheeler. You have two discussion sections. So section 101 is in 3108 Echeverry. That room can actually hold 70 people, and I guess the scheduling system is allowing that room to fill up to 70. I recommend you don't let that happen. It looks like it hasn't happened. I think there's 37 in that room right now, and there's 20-something in the other room, which is 293 Corey Hall, which I think are good numbers for these discussion sections. For discussion, you'll get a sprinkling of both your TAs. So every 2 weeks, Travis will do the discussion, then Yang will come in and do the discussion, then back to 2 weeks, Travis or so. So you get to know both of your TAs. The reason why we're doing that, where it seems Travis has a heavier discussion section load, is mainly because we only have 3 labs right here, and we have to divvy up the work between the 2 TAs. So actually, you can see here from the different sections for lab, Yang's got 2 of them, Travis has got 1 of them. Okay, so depending on which section you're enrolled in, this is who your TA is. Okay? Office hours, I think I've already told you the office hours. That's the primary mechanism for visiting us. I do get a lot of students in my office hours for this class, so don't be shy. Come to office hours because a lot of other people are. All right? And this is the type of class where office hours can be very helpful, because there's a lot of things you learn in lecture that you just will not get out of the book. Okay, so there's a lot of intuition. Circuit design is intuition in a big way. If you think about it, a circuit designer is someone that just knows a lot of small things, memorized a lot of small things, and then can immediately look at a big circuit and say what it's doing. Okay, because you recognize things. Circuit design is kind of a recognition game, and to learn how to do that takes a lot of practice. But it really helps to talk to someone about it too. You won't get it out of a book, right? But you can get it out of another human being who's talking to you, showing you how to look at things, that helps you to do things faster in circuit design. So it does make a lot of sense to visit us in office hours, and I do recommend you do that. I have this course description thing here. I guess I went crazy and wrote something quite long. You can read through it if you like. It's basically saying that digital seems to rule. Well, I guess I'll say a few things about it, right? Digital circuits seem to rule the world right now because you got your CPUs, a lot of your cell phones and that sort of thing now can do a lot of computation. And digital does rule in a big way. All of the technologies that people are using now to make circuits are really honed for digital. So So that makes it more difficult for the analog designers. What is digital? What is analog? Digital is like a computer. So it's treating computation as ones and zeros. Analog is actually handling the actual signal you see. So if you have a sinusoidal signal, it's not breaking that into pieces. Okay, it's handling all of the signal in a continuous fashion. Turns out that analog is still extremely important. And for most of your favorite applications, it may be the most important thing. For example, in your phone, right? Most of you now are basically living off of your phone for your data and et cetera. But all the wireless stuff that you have in your phone, at least for now, is analog. The front end, all of that stuff that receives the electromagnetic waves, that converts them, down converts them to lower frequencies where digital can then handle them, all of that is still analog. And it's probably going to be true that that's going to be analog for a long, long time. Of course, there's people thinking of trying to implement all of that in digital. But if you try to implement all of that in digital, at least today and probably 5 years from now still, maybe 10 years from now, that's going to cost too much power. So what would you rather have? A functional phone that's perfect that lasts 1 minute on your battery, or a functional phone that's still just as perfect that lasts, however long your phone lasts, 4 days or something. Okay? That's why analog is used in a lot of applications. It can consume less power at the very high frequencies for things that interface the real world to the digital world. Okay? And that's what a lot of this stuff says right here that I've written here. But you can go ahead and read that if you like to read, I suppose. So prereqs for this class. This is kind of a stickling point here because of the makeup of the courses that come before this class. So the prerequisite for this course is EE 105 and some aspects of EE 20N. Okay, so I would assume that all of you have taken these courses. If you have not, you want to talk to me. Okay, so the more important one is 105, I would say. But 20N would still be important because you want to understand some things that have to do with signal processing and frequency selection, that sort of thing. So some of the topics that you should understand: basic network theory. So how to do nodal analysis, KCL, KVL, to solve a circuit. You should all be able to do that. Some basic linear systems theory. So if I represent an amplifier with a block that has a transfer function h of s, and I put in a signal s sub I of s into that thing, right? You should understand how that works. Okay, you should understand to some extent Fourier transforms, Laplace transforms, maybe not both, but just an understanding that there's a frequency domain and there's a time domain. Okay, you should understand that there's those two domains because we're going to be working in both of those domains throughout this course. Use of small signal models in the analysis and design of bipolar junction transistor and MOS amplifier circuits. Okay, so you should understand how to do this at a rudimentary level, I guess at the level where you can analyze single and multi-transistor amplifiers with these types of devices, including common emitter, common collector, common base, cascode, that sort of thing. Those are things you should have seen in your 105 class. Then finally, elementary semiconductor physics and device operation for things like PN junctions, bipolar transistors, MOS field effect transistors. That's also something you should have gotten in 105, if not a little bit in 40 as well. And so here's where the stickling point comes, because there's a lot of different people who teach 105. Right? Some of you may have got 105 from Professor Piester. Some of you may have got it from Professor King. Some of you may have got it from Professor Salahuddin. And so they teach it with different perspectives. I know this. So Piester will teach it in a much more circuit design aspect. Okay, so he'll really emphasize more transistor-based analysis, at least I think. Is that true? That's true. Okay. Salahuddin, I think, emphasizes more the device physics part of this. Okay, so which is more important for this class? Well, they're both important for this class, but I would say the circuit design aspect is more important because, right, this is a circuit design class. Okay, but this class takes circuit design to another level than 105. Because in 105, you already know how to analyze some rudimentary transistor circuits. We're not only going to create much bigger circuits than you've done in 105 and analyze them. By the end of this course, you're just going to be able to look at it, snap your fingers, and in 30 seconds, you'll know what it's doing. And you'll be able to tell me quantitatively what the gain is, what the impedance is, what the frequency response is, very, very quickly. So if I'm successful, you're able to do that by the end of this class. And that is a huge skill to be able to learn. Okay? But the other complexity we add to this is we're also forcing you to become more understanding of the devices as well. So it's not just going to be we're going to draw a circuit for you. It's going to be we're going to give you some of the device sizes, like the W over L ratios of an MOS device. You're going to have to know how big the source and drain should be for that device. You're going to have to be able to calculate the capacitors associated with the source and drain and include that in your analysis for the circuit. Okay, so that's the device complexity we add into this. So there's both a device, increased device level, and increased circuit level understanding that you'll get here over what you got in 105, despite which 105 you took. Okay? I will be assuming some knowledge when I teach the parts in this class that are sort of repeats of 105. So I will review some of the stuff, but I'll go through them very quickly, assuming that you already know the stuff. Okay? And that might even happen by the end of today if I get there, when I start talking about device models. Your textbooks. Okay, so last time I taught this class, I taught it with the second textbook here, which is written by Behzad Razavi. It's actually a very good textbook because people say it's easier to read. Okay, so this is the Razavi textbook. This is not your required textbook. Okay, we're calling this your supplementary or recommended textbook. It's good reading because it's somewhat simple reading, but it reads best for someone who already understands the material. So you argue that maybe it's not that great a textbook. But it's very concise and gives you the information very, very quickly. Okay, the textbook that we will be using is this textbook here. This is Gray and Meyer. It is you may know that Paul Gray and Bob Meyer are professors here at Berkeley. They're both retired now. But this has been the mainstream textbook for many, many generations for circuit designers. This is a new edition of it that updated it to include more MOS design, which is more relevant today. So this is the textbook we'll be using. This textbook is actually a much better textbook to have as a reference because it goes through a lot of detail. Okay, so the device physics is actually very good in here. You know, it does it in 2 chapters, but I would say it rivals what's taught in 130. Right? It summarizes what's taught in 130 very well in just 2 chapters. They do such a good job of writing that stuff up. The other things, it's much more detailed in terms of showing you how a circuit will work. Okay? Razavi makes a lot of approximations, which actually is a good thing, as I'll tell you in a second. The only way you're going to be able to analyze a circuit in 30 seconds, like I'm telling you, is to make approximations. Okay? Gray and Meyer do make approximations too, but they make fewer so that you can see more of it. And I guess they rely on your laziness eventually to approximate some of these things instead of going through all the work there. But they at least show a lot more stuff. Okay, so that's why this is both of them are good text, but we're using this one partially because it's Gray and Meyer, right? This is Berkeley, it's Gray and Meyer. We've got to use this one, right? There's really no choice, right? Those on the internet will love that. Okay, so those are your textbooks here. There's a bunch of other suggested references I have here because, again, circuit design is practice. You become good when you spend a lot of time at it and you practice it. And if you want to see more and more examples of circuits you can solve, there's other textbooks out there. So I've listed a bunch of these textbooks here, and I'm going to get these on reserve at the library, the engineering. Is the engineering library even accessible right now? It is, okay. Because I know it's under construction or so, but you could still okay. Well, these will be on reserve in the library too, in case you want to get them, find a few more problems to solve for circuit design. And I got a very long list here. Okay, so reading assignments. So this takes us to your syllabus. Let's go to that other sheet that you have, the syllabus sheet. And so this is a pretty detailed syllabus of what we're going to be doing in this class. So just some of the headers here. So you got dates in this column. You've got material to be covered, just small topical descriptions. Along with the material to be covered, I have sections of your books that you can read that talk about these things. So this is Gray and Meyer right here. G&M stands for Gray and Meyer. R stands for Razavi if you want to read that book. I would recommend Gray and Meyer, but if you find you like Razavi, I've got those sections there as well for you. And so it pretty much goes through all this. I guess the first things I want to point out is that these stars that you see next to these dates here, and I guess there's some near the very end there, those are dates when I'm not going to be here. So the first thing to notice is I'm here today, but I'm not here on Thursday, and I'm not here on Tuesday next week. Okay, that's not a good way to start off the semester, but I pretty much start off every spring similar fashion because I've got some conferences that I'm organizing that I have to be at certain organization meetings for these things, and I just have no choice for this. So I'm gone these 2 days. What we're going to do these 2 days, at least on the 20th and 25th, is your TAs are going to lecture because that's review material for you. Okay, that's material that's going to go through the basics of bipolar junction transistor modeling and some of the physics and MOS modeling. All stuff you should have seen in a previous course, but that you need to be reviewed in order to do well in this class. Okay, so that's what's going to happen on the 20th and 25th. So Travis will lecture one of those. Yang may lecture one of those. Did Yang leave? He left, yeah. Did you guys decide who was lecturing?
I think this week, me and next week.
Okay, all right. So you got Travis this coming Thursday here. And then I'll be back on the 27th, but lo and behold, you could see just another date there. On the 1st, February, that's a Tuesday, I'm not going to be here for the actual lecture period. I'm basically flying back that day. So what I'm going to try to do is reserve a room, maybe this room, for sometime later in the day, like 5 o'clock or so, and do the lecture then. And the nice thing about this webcast thing is that I don't have to check and make sure that all of you can make it, because if you can't, you'll still get it off of the webcast. All right, so in general, I'll try to do the lectures because, you know, this is an important lecture right here. There's a lot of intuition that I'm teaching right there at this point right here. So these other lectures here, this is review stuff, but, you know, this lecture on the 27th, it's important that I do it, I think, because this is where I'm hitting you with intuition that's going to be important for the rest of the semester. Okay, so if you're going to miss any lectures, don't miss that one. Try not to miss this one, but you can at least watch the webcast. I'll warn you about the webcast. There's been some complaints about it. It's not a perfect system. So if you think you're going to miss a lecture and see the webcast, that's a little bit of torturous for you if you really want to see the lecture, because I've heard complaints about the fact that the sound is in phase, is right on time, but what's written is delayed from the sound. And so picture trying to watch a lecture where I'm saying something and you don't see what's being written until 30 seconds later. That's not that's not fun. So don't rely on the webcast necessarily. They're only there as a safety belt for you in case you can't make a lecture. So what are we talking about? So we talk about device operation in the next lecture. We'll talk about inspection analysis. So there's where the intuition comes in. Right? I don't know how you're analyzing transistor circuits right now. If you're actually writing out the whole small signal model and then solving that using KCL, KVL, that's a waste of time. Okay, you learn that because you have to learn the small signal models. You have to understand what small signal is happening, especially when you get hit with a new device like a mechanical device or so, that you have to put a small signal model down for. Those are very general techniques, the small signal stuff you learn in 105. But here, we'll still use it, we'll still pay attention to it, but you're almost going to forget about it. You're almost going to solve these circuits by looking at the transistor, not equating it to a hybrid pi model or something like that, and just analyzing the circuit by looking at transistors. Okay, that's what I'll be teaching in these lectures here. We'll be able to do a single transistor amp very quickly, tell what its gain, frequency response, input and output impedances are. Multi-transistor amplifiers we'll get to. These are the same amps you've seen in 105 that we're going to be doing inspection analysis, which means you're going to know what they're doing like that. You'll get that talent if you don't already have it. Okay, then we're going to start talking about active loads. So instead of just resistive loads, we'll start using current source loads there. We'll actually talk about current sources and some more advanced current sources than maybe you've seen in a previous course called a high swing current. Towards the end of the class, we'll look at band gap references and other types of sources that are very stable against temperature and supply variations. We'll then go into op-amps. And you'll see in this syllabus here, op-amps is a big part of this course. Okay, so this course, if you really wanted to gel it down to just one sentence, it's the study of how to design op-amps at a transistor level. Okay, op-amps are probably the most important type of circuit block that you can have in any analog circuit. You see them everywhere, and I'll show some examples at the end of lecture today. But you see we spend a lot of time on op-amps, how to design these things. These are basically diff pairs with some gain. The same op-amps that you played with in 40, maybe even 104 as well, but now we're looking at the innards of these things. How do you build one of those things so that it does what an ideal op-amp you already know does? After studying op-amps, we then take a look at some more involved topics like stability of op-amps, when you put them in actual feedback circuit. And so along with the stability comes this thing called compensation. You can't just build an op-amp, but you have to actually add capacitance or some kind of reactance somewhere in the circuit to make sure that once you hook it up into a feedback loop, it doesn't just start oscillating. It doesn't go to a rail or so, that it behaves itself. Okay, so stability is a big thing, and we'll spend some time talking about compensation, which is basically the art of making sure that your circuit is stable. And you do that by adding capacitance in certain places. We'll talk about other features of these analog circuits that are important: slew rate, settling time, and then finally we get to feedback. Now feedback I consider a very important topic. This is something you learn in many different courses. So if you take things like 128, the controls class, that's all about feedback and root locus and that sort of thing. We hit you some more in this class with that, but we do it in a much more practical sense. So you're no longer doing feedback with block diagrams. You're doing feedback with actual transistors and actual elements being put in the feedback loop. And that's a more difficult thing to do. So you're going to learn an actual practical skill that if you learn feedback correctly, you'll find that you can solve tons of problems in all sorts of different fields, not just this circuit design field, but MEMS, chemical engineering, bio, all of these things. Everything is a feedback system. And this is a class where you're really going to be able to learn it very, I would say, correctly. You'll learn protocols for handling almost any feedback system. Finally, at the end, I mentioned this before, we get to some advanced topics with the supply-independent biasing, temperature-independent biasing. This is where I covered band gap references. And it used to be that this course could cover more stuff, but now we've lost this week here. And so I've adjusted this syllabus to account for the fact that we lose the last week to reading, review, and recitation, right, which is a good break for you guys, I think, but it does take away from some of the lecture material. Okay, so in a nutshell, this is what we're going through in this class. I'm also, in addition to all of this, showing you when your homeworks are due. So all of the lines after the bolder line here, these are all Tuesdays. So you can see I've already planned that all your homeworks are due on Tuesday. You will not get a homework this week. You will get your first homework assigned on the 25th, one of the days that I'm not here. Okay, and that homework will be mainly about device models and sort of things that you should already know, just to refresh your memory on those things. So in addition to homework, let me point out the exams here. So there's only going to be one midterm exam in this class, and there's going to be a final exam in the class. There's pros and cons to having two midterms. I used to have two midterms in some of my classes. I shifted to one now because you also have a project in this class, and the final counts pretty heavily. So your midterm is going to be on the 17th of March. Okay, so that's right before spring break. So you take that midterm, and then you relax. And you get it back, and you forget about it, and you get it back on Tuesday. Okay, so that's kind of a nice thing, right? But we're going to pretty hold steadfast to that. The midterm is going to be in this classroom, unless you feel it's too stuffy in here, in which case we could try to find another classroom, which would then have to be in the evenings, okay? So I would recommend doing it in this classroom if we can, but there's a lot of people in here and not a lot of seats between people. So we'll decide once we get closer to this date here. Your final exam as well, we're in exam group 15, and I'm just going to hold to that exam group. Okay, so we're not going to have an early exam or something like that because that always screws with someone's schedule or that. We're going to hold to the exam group. Exam group 15 means the final is on Thursday, May 12th from 3 to 6 p.m. Okay? And I guess you're seeing one more thing on this syllabus here, and that's labs. So this class, of course, has labs, but it's kind of different from your other courses in that it's not as rigorous as your other courses. Like 105, these other courses, they may have had labs almost every week. In this class, you have a total of 4 labs. On the last lab, we may not even do. Okay, so what does that mean? That means that your first lab, so you got no labs for the first 3 weeks. Okay, your first lab comes in for single transistor MOS amplifiers. This is mainly a simulation lab. And for simulation labs, you're doing those all on your own. Okay? Then you get your second lab, which is differential pair analysis and design. That's actually a hardware lab. So you're actually going to hook up a pretty much an op-amp on a board. Okay, it's going to be a pretty crappy op-amp because it's on a board. And we're going to be using bipolar transistors, but it's a great thing to learn how to do. Right? If you get this kind of experience, you get some of the hardware experience that you should come out of a class with. You know, you learn how to, well, you should know how to do it already, but learn how to debug with oscilloscopes and that sort of thing, a larger circuit of transistors that actually can be compensated and operates just like any op-amp. It's just that its frequency is very low versus what you can buy off the shelf these days. But that's what this lab is. In this lab, you will be paired up with someone. So you should have a partner for this lab. And I'll talk about that in a second as well. Then the third lab here is really disguised. It's a lab, but it's a disguised project. Okay, so your third lab takes a number of weeks here. You can see it starts about March 15th or so. This is a project. This is something where we're giving you a spec that you have to meet for a particular circuit. Could be an op-amp, could be all sorts of different types of circuits there. And you have to meet the specs. And you're going to do it all through simulation. And it's going to require that you understand how to design. This is not something where you're given the topology for the thing. It's completely open-ended. You use whatever transistors you want as long as you meet the specs. And you're going to find that you can't use any transistors you want. You're going to have to really design this to be, there's going to be a number of different designs that work. But you can't just throw transistors, of course, on a piece of paper and it works, right? This is something you will have to design. It's going to take a lot of time. And this is going to compete with the projects in your other courses for your time at the end of the semester. So by the end of the semester, I look out at the class and I see people doing a lot of this, and I know why that's happening, because you've got projects on top of projects or so. Unfortunately, maybe fortunately, right, this is one of those classes that will do that to you, and you may think it's a bad thing, but when you get older like me, you look back and you say, wow, that was great. You will say that. Lack of sleep was a cool thing, right? Because you can't do it when you're older. You could do it now, right? And you should. Yeah. That's solo. Yeah, we do that solo as well. Any simulation-based thing we do solo. You want a partner? That's negotiable, I guess. But we'll see how it is when we get there. But right now, I think it's better for it to be solo. Okay. That way, everyone turns in their own report and that sort of thing. No one gets mad at each other for not doing enough of the work and that sort of thing. Although that's an element that we have to emphasize in some of the courses. So you at least have one lab where you have a partner, where you get to experience all those things, the good and the bad. Right? I'm not saying it's all bad, right? There's a lot of good, too, with that. Okay, so those are your labs. So lab 4 is a feedback lab. I have some question marks there. I have the lab prepared. We're ready to do it. We've never done it. Because by the time we get to the end of class, there isn't enough time to do it. People are too busy working on their projects and that sort of thing. We sort of gauge it by where you are on your projects. Okay? And so it exists. And I can hand it out in the end, but whether we do it or not depends on, you know, how many people are falling asleep in class, that sort of thing. Yes?
What's the due date for the project?
The due date for the project is going to be right. Usually, each of the labs are due sort of the Tuesday after the last week of it. So theoretically, it would be right here. But of course, what I just said, right, it could shift a little bit if we don't do lab 4. Okay? Don't rely on that, though. Be working on that project from the very beginning. You don't want to be one of those really pulling all-nighters, which you'll probably do anyway because of your other classes. It's your other classes that are the problem, not this one. You'll probably, yeah, you'll have some late nights for this project, I'm pretty sure, okay? All right, so let's get back to the information sheet and finish that up. So I talked about your problem sets. You see when they'll be handed out, when they'll be due. I already mentioned that they should be turned in on 5 p.m. on Tuesdays. They should be turned into the EE140 box in the Corey Hall Lounge. So there's a box in there with a slit in it that you can slip your homework in. It has to be in by 5 p.m. because we'll pick it up right at that time on Tuesdays. Okay? I think you all know where these boxes are there. So here's some stuff on the lab here. I kind of already talked about that, so I don't know that I'm going to say a lot more about the lab and this. I said that there'd be a CMOS design lab first. Maybe one thing that I could talk about, you'll get this from your TAs too, is that the lab reports are required after the experiments. The due dates for the reports are announced when the handout is passed out. So in general, they'll be due when I said, right, just the Tuesday after the last week of that lab there. We may want to change that because if there's a homework due Tuesday, maybe we'll make them do Thursdays or something instead of Tuesdays, so you don't have two things happening at once. But for labs conducted in groups of 2, each of you will turn in a separate report. Okay, I guess that's one lab conducted in groups of 2, unless we do the feedback lab, which is a 2-person lab as well. For those, you each turn in your individual report. It's not one report per team. So that's that. You can read through the rest of this here. Probably the other thing I should show are the points for the lab. And so you can see they're weighted differently. Lab 1 is not a very difficult lab, so it's worth 200 points. Lab 2 is a little bit more difficult because you actually have to hook up hardware and get things to work. That's 300 points. Lab 3, which is really your project, is 900 points. Okay, so you can see how that divvies up. And so, you know, the whole thing is 1,500 points, provided we do Lab 4. All right, but then how does this whole thing fit into the whole grading scheme for the class? Well, here's how I'm going to do the grading here. Your problem sets are going to be worth 15%. That's not a lot. And the reason why I do that, because I know that there's a lot of, if we will assign some problems out of the book. I know there's a lot of solutions already floating about there. You just have to Google it or something like that. Why am I even telling you how to do that? I guess it doesn't matter because you already know how to do it, right? But, you know, there's a lot of solutions out there. We'll also be making up some problems where there'll be no solutions to that, so you really legitimately have to do those problems. But the reason why I make this 15% is to make it such that you're not afraid to do the problems on your own, right? I mean, so what if you get it wrong? Try to do it on your own rather than looking at something else out there. Try to do it on your own because, again, for this class, practice really makes a difference. If you don't practice, you're not going to be able to do what you need to do well in this class. Okay? Laboratory and project, so sort of the labs or the project is contained in the lab, that's 30%. So that's a pretty good chunk of the grade there. And you can see how much that project is worth in this class. The midterm exam is worth 25%, the final exam worth 30%. Okay, so that's how I break down the grading. I guess I said things about the midterm already. Just want to make sure I cover everything. Computer accounts. Okay, so computer accounts, let me pass those out right now. So all of you probably already have computer accounts, but the question is, do your computer accounts access, hold on a sec. Do your computer accounts actually access all the software that you need to use in this class? And so since that's always questionable, what's going to happen, I think like the rest of your other classes that you're taking, is I'm passing out actual computer accounts here. You'll see your account login, the password for that account, which you can change once you log in. Okay, so I'm going to pass these around, take one, and that's going to be your account for this class. One more thing, and that's the grading thing. So there's the grade info. I guess I'll say a few things about this now, and then I'll say a lot more about it later on. Trying to figure out how to get this thing back in on screen so I can move it around, which I can't right now. And I don't want to open this because then it'll screw up my how I align things. Anyway, this is the grading procedure. You have this sheet in front of you. What I do is I do what's called a Z-transform. Okay, in a Z-transform, you'll get a particular grade. So maybe this is an exam or something. That's G sub I. Okay, and then the whole class will have an average G sub average, and the whole class will have a standard deviation sigma sub G, right? This is statistics that you'll remember, right? Standard normal distribution. Statistics, very important stuff, right? To me it is. I'm not joking about that. I think you should be taking a lot more statistics than you do. I say this in all my classes, actually. But anyway, in this, what this does when you put this transform on your actual grade, is it turns whatever numerical score you have into something that tells you where you stand versus the rest of the class. So this basically, if after you do this transform you get 0, that's the average for the class. Okay, if after you do this transform you get 1, that's 1 standard deviation above the class. So by just telling you what your z is, that tells you where you stand in this class. Okay? And so at some point I'll be able to tell you what a 1 means in terms of grades. Okay, 1 is probably going to mean an A in this class. But the big question is, where's the A minus, where's the B plus, and that sort of thing. That's where people want to know. We'll talk about that after your first midterm, okay? So we won't talk about that now. But I'll take Z's for all of your different areas of this class: homework, midterm, final exam. Your lab actually has some complex Z formulation here, which you can look at your leisure. You can see I'm just weighting these based on the total points in the different labs. Okay, this creates a lab Z that then I have to take one more Z on that lab. And I actually take Z's per TA as well, because your TAs may grade differently. They'll be grading your labs. They may be grading differently. They may be telling you different things there. So I don't want, say one TA is teaching better than the other. Not that that's necessarily going to happen, right? But I don't want that to factor into the grades either, right? So this Z thing even averages that out. So it's a good way to do the grading as long as you guys understand how these Z formulations are being calculated. And after the midterm exam, I'll actually show you my spreadsheet. You can see what your Z's are. You can come to my office and get all that information as well. Okay? So that's how grading is done in this class. So any questions regarding anything for this class up to this point? Office hours, room locations, any logistics? Yes? Yeah, you're going to be using SPICE mainly for simulations. We're not going to do any layout in this class, so you won't need cadence and that sort of stuff. Anything else? All right, so let's go ahead and start with the lectures. And this is pretty much how I'm going to be doing the lectures. So you can see this little screen that I have. What I like to do is divide everything up into 2 screens. And the reason why is because I could have, say, some circuit drawn right here, and then use up the rest of this screen down through here, and you no longer see the circuit that we're working with, so I can't refer to it again. Okay, by using 2 screens like this, I can keep the circuit on this side and then start writing on this side and continuing to refer to the circuit on the other side. It's kind of the same thing as having 2 chalkboards, which you lose when you go to this computer display, but I regain it by just having these 2 pieces there. I guess I wish the screen were bigger, but I guess I'll ask you right now, is this big enough for all of you to see, even in the back? I'm seeing nodding yes. Okay, wait till you see my handwriting then, and then you can decide after that. Okay, so we've gone through the information sheet. So what I want to do right now is just start talking about op amps. So things that you should know already, because after all, op amps are pretty much what this course is all about. I see. Let me do one more thing here. Okay, so let's do a review of op amps. And op amp circuits. Right, so first of all, what do we know about op amps already? Let's just review that. So you know the symbol of an op amp. You know that it's going to look something like this. It's a triangle, and it's got minus and plus terminals. So there's a minus terminal. There's a plus terminal for this op amp. And if I explicitly want to draw those terminals, I'll do that here. So I've got these terminals there. And this is generally going to be my output voltage, which I'll take right there. But what's inside of the op amp? So right now, what you should know is ideal op amps. You should know that if you put a voltage here, so I'll call this V minus, and a voltage there, V plus, then the output of this op amp is really going to be the same as what would be produced by this voltage-controlled voltage source here. And so this symbol that I'm using right here is a symbol for a voltage-controlled voltage source. You've all seen that symbol before? Triangular symbol? Excellent, good. Okay, so you have that voltage-controlled voltage source, and the value of that voltage-controlled voltage source is going to be V out is equal to some gain A times V plus minus V minus. Okay, so you already know that these op-amps are performing some kind of differentiation function. Differentiation means you're subtracting the two input signals from one another. Okay, that's an important thing with these op-amps. Okay, so I guess I could finish the picture and actually put some voltages here. Let's call that V2. Let's call that V1. Okay, and so this is an ideal op-amp. So specifically right now, I'm talking about an ideal op-amp. And that's the most basic type of op-amp we can talk about. This is what you learned in 40. In this class, what we're going to learn about is why op-amps are non-ideal and how you can try to make them more ideal by using certain different circuit topologies. Okay? And the closer to ideal you can get, of course, the better your circuit is going to work. But before talking about all that detail, which we'll spend the whole class doing, let's see if you can list for me the properties of ideal op-amps. Okay, so if this is an ideal op-amp, what are some of the things you can say about it? Anyone? Yeah, so one of the things is the output impedance equals 0. Excellent, good. What are some of the other things? And what does that mean, actually? If it has 0 output impedance, what does that mean? That's right. It can drive pretty much any load without any problems. Okay, that's great. That's part of the ideality of this. Okay, let's look for number 2. What else do we know about ideal op-amps? Yes? Gain is constant across frequencies, yes, so it has infinite frequency response. That's not usually one of those things listed as the ideality of the op-amp, but I'll accept that because that's a good one. Okay, so I'll say it's an infinite frequency response. It goes out to infinity with the same gain. But when I talk about an ideal op-amp, what am I talking about in terms of gain? It's infinite, right? So not only does it go all the way to infinite frequencies, the gain is also infinite. It's not a constant value. It's up there in the clouds, right? So I can write down that A is equal to infinity. Okay, that's actually a big thing too. And we'll talk about why that's a big thing in just a second. But before doing that, what's the last one of these things that I could say? Exactly, yeah. So the last one that people usually will specify also is that the input impedance, Ri, is also infinity. And so the way that I'm going to do that, well, let's take advantage of what we have here, which is color. Okay, so there's my input impedance there. This is the output impedance. And hopefully you've seen this kind of notation before. When I do those brackets with the arrows, that means I'm looking in that way into the circuit. Okay, and when I look that way into the circuit, I see Ri as my input impedance. When I look this way into the circuit, I see R naught as my output impedance. Okay? And so, what are the consequences? So we already talked about the consequence of R naught, right? You can drive any load. But what are the consequences of A being infinity, the gain being infinity, and the input resistance being infinity? Okay, first of all, input resistance being infinity. What does that mean? Exactly. So there's no current. So if I had to write the current going here, I minus is equal to 0. Okay, and I plus also has to be equal to 0. That's a big thing. That's one of those things you use when you analyze a circuit that includes an op-amp. Okay? What's the other thing that we can say? So let me write that down here. So this means that I plus equals I minus equals 0. Okay? How about gain of infinity? What does that give us? Yeah. Exactly. That's good. Okay, so what that says is that V plus is equal to V minus. Okay, but is that always the case? When is that not the case? Exactly. So this is only the case when you're assuming that V naught is finite. Okay? So if you have infinite gain, and if V naught is infinity, then V plus doesn't have to be equal to V minus. But if you have a finite output, right, if V naught is finite, and you have infinite gain, then you have to have 0 volts between V plus and V minus. Okay? And so the way that you figure out whether that's finite is exactly what you said, which is negative feedback must ensure this. Okay, so the first thing you have to check when you do an analysis of an op-amp circuit is to make sure that the feedback is negative feedback. Because you can hook an op-amp up in all different ways, and you can end up with something where the op-amp is actually in positive feedback, in which case none of these rules, actually some of them, maybe the R naught is 0, the Ri is infinity or so, only some of these rules will hold. But all the other rules, and probably the most important rule, which is that V plus equals V minus, that no longer holds if you do not have negative feedback. Okay, so the best way to explain this is through an example here. Let's take an example that you're very familiar with now. Whoops. I don't want that. And that's the example of an inverting amplifier. Okay, so you all know how an inverting amplifier is hooked up. This is something where there's your minus and plus terminals. We're going to ground out the plus terminal. The minus terminal, we're going to put feedback to the output here, maybe with a resistor R2, resistor R1, and our input signal VI will be right here. Okay, so that's our inverting amplifier. You should know this circuit. By the end of this class, you're going to look at the circuit very differently. So right now, you sort of see it as an ideal op-amp circuit, but in actuality, if you want to be more technical about this, after you learn feedback, this is a shunt-shunt feedback circuit. And this is actually not a voltage amplifier, it's a current amplifier. Okay, so what it does is it amplifies current that goes into this node right here. That's the right way, I suppose, to look at this circuit. And by the end of this class, that's how you will be looking at this circuit. And in 240, if you ever take that class where you have to deal with noise, you're really going to be looking at the circuit that way, because you have to interpret this as a current amplifier in order to really understand how the noise performance works. Noise is something we won't cover in this class, though, so not a whole lot to worry about. But let's analyze this circuit. So the first thing you want to do when analyzing this circuit is verify that there is negative feedback. Okay, and so a good way to verify that, it's obvious that this is, right, because you've seen this circuit before. But a good way to try to verify that is that if I take a voltage and I have a perturbation in that voltage, say delta V at the input going up, what's that going to do? That's going to create a perturbation across this resistor that also goes up. Okay, that's going to create a perturbation at the output. Since we're going into the negative terminal, that perturbation is going to go down, right? So basically, I've gone up there from here to here. I've created this voltage that goes down. That now feeds back a downward going signal here, so that pushes this back down. Okay? The fact that it's pushing it back down basically means that we have negative feedback. Okay? So that's one very quick way to look at this circuit and figure out whether it's negative or positive feedback. Okay? I think that, maybe a better way to do this is just take the example, what if we did this? So what if I, instead of putting the resistor there, stuck the resistor around here? What if I did that? Okay, so if I went ahead and I took a voltage and made it go up right at that point there, that's going to the positive terminal here. That makes that voltage go up. Across here, that's going to return a voltage going up. And so what's going to happen to this signal? As a function of time, the output voltage is just going to rise up. And usually there's going to be a maximum voltage that this can go to, so it's going to hit the rail. Okay? So this is an example here of positive feedback. If we have this, then the ideal op-amp rules they don't hold. Okay? So anyone can throw a trick question at you and hook something up in positive feedback, and you go through and analyze it like it's an ideal op-amp circuit. It'd be completely wrong if you tried doing that. Okay? So the first thing in any of these circuits is test and see if it's really negative feedback. Okay? Whenever you see a new circuit. All right. So after this, so we verified that we have negative feedback there in the original circuit, and we showed an example of how positive feedback looks like. So this was a positive feedback example. Let me go back up here so we see this. Let's continue with this problem here. So we verified negative feedback. So the next step was we try applying our ideal op-amp rules to this circuit. And so the ideal op-amp rules do a lot of good for us. So 2, if there's negative feedback, then we can say that the output voltage, so I'll say check, we have negative feedback, then I'll come down here and say, therefore I could say that my output voltage is indeed finite. If my output voltage is finite, then V plus equals V minus. Okay, and what does that tell me in this circuit? V plus is at ground. Okay, what that says is that the voltage at V minus, which is this node right here, that also has to be ground. So that's 0 volts. Okay, it behaves in all respects like ground. Okay, so if there was a larger voltage here, then across that resistor you'll see a voltage drop of whatever this voltage is minus ground. Okay, and because that resistor sees that drop across it, current is going to flow across it exactly by the expression V is equal to, or I is equal to V over R, right? So I can immediately start writing some expressions, but first let me just say that this means that this node is a virtual ground. So the terminology we use to describe that is virtual ground. I'm sure you've heard that before. The power of virtual ground is that it removes almost anything that's attached to that node that could be a parasitic. So in a lot of circuit design, and we'll talk about this later on, in a lot of circuit design we have stuff that we don't want there. So say there's this capacitor there that's sitting right there. Because just, there's capacitance everywhere. If I hook up this circuit and this is an ideal op-amp, then because of the virtual ground that I have here, that capacitor is eliminated. Because there could be no voltage drop across that capacitor. There could be no voltage changing across that capacitor. It's as if it wasn't there. Okay, so this is a great circuit to use anytime you want to measure very small signals, very small currents. And I'll say in MEMS, where we have very small devices, you have to have extremely sensitive circuits to detect their motion. This is one of the best, okay, because it kills the parasitics that can compromise a lot of your measurement of these devices. Okay, so that's a little aside that you have that virtual ground. But with this, once I'm able to say this, that V plus equals V minus, I can now solve this circuit with no problems. Okay, so let's do that. Whoops. Okay, so 3, let's start actually solving this circuit. Is that a dark enough green for you? I think it's dark, okay. So what can I say? All right, so I know that these two are the same, but I also know one more thing. I know that this current, I minus, that has to be equal to 0, right? So any current that's generated by this input voltage, it can't go into the op-amp. Right? That means that any current generated here that flows there doesn't go into the op-amp, but has to flow up through the feedback resistor. Okay? And if that's the case, then I can write some expressions. I minus equals 0. That means that if this is I1 and this is I2, for current going through resistor R1 and current going through resistor R2, then I have to be able to say that I1 is equal to I2, because no current can go into the negative terminal of the op-amp. If that's the case, I can immediately start writing equations now. So I1, I know, is whatever voltage drop is across this R divided by this R. Well, that voltage drop is VI minus 0 over R1. That's VI over R1. And I also know that because I1 has to be equal to I2, has to be equal to I2. Okay, so I now know the current going through resistor R2. Okay, but that current going through resistor R2, because this node here, can you see when I'm, can you see my little dot that I'm pointing with there? Barely, I suppose, yeah. I don't know a better way to do it without going out of pen mode. Label my nodes. That'd take too much time, though. Yeah, the other thing I can do is, I can use more props up here. So that's 0 volts right there, right? Problem is you won't see this when I'm on the webcast if I use this laser pointer, right? But people have told me they don't see this little dot anyway on the webcast. So you have 0 volts right there. But if I have 0 volts and current going up that way, there has to be a voltage drop across R2 as well, right? And so that voltage drop I know is just going to be the current times that resistance. So that means I can write an expression for the output voltage V naught, which is going to be 0, which is the voltage on this side of R2, plus the voltage drop across R2. Because the current is going in that direction, the voltage drop is going to be negative, right? And so I'm going to say that's going to be minus the current I2 over R2, right? Which means that that voltage at the output is minus I2 over R2. Okay? And so I can now combine all of this information here to say that my output voltage is going to be minus, and I know what I2 is, which is this VI over R1, that times R2. That means this is equal to minus R2 over R1 times VI, and therefore the transfer function V naught over VI is equal to minus R2 over R1. Okay, so all of this stuff that I just talked about you should already know, okay, but I'm just sort of jogging your memory on how to use an ideal op-amp, how to analyze an ideal op-amp, and why it is that we can analyze ideal op-amps this way, where we could say that the current is 0, the voltage drop between the plus and minus is 0, the gain is nearly infinite. What you'll learn by the end of this class is that even though this op-amp may not be ideal, when you put it in feedback like this, and it's negative feedback, the feedback pushes it closer to ideal, actually. So there's a lot more things going on than you're seeing just through this analysis here. Feedback actually idealizes your op-amps for you. if it's negative feedback. But that's a concept we'll learn way at the end of class here. For now, let me just talk about the fact that, we've talked about these ideal op-amps here. Op-amps are not really ideal. Okay, so here are the ways that they're not ideal, right? So one, they have a finite gain, A0. Okay, so this gain is not infinity. We want it to be a very large number. If it's 1,000, if it's 10,000, that's great. If it's 50,000, that's great. But if it's 10, that's not too good. All right? Depends on your application, though. Now, let me ask you this question. Does it matter whether it's 10,000 or 11,000 or 9,000? Does it matter? Yeah, good. Some of you already have the right attitude, right? So what you want to be able to do is not be too exacting about your calculations. That's how you do things fast, and you need to do that for circuits. So in some classes, some areas, you have to be exact, right? Like in physics or so, you want to calculate a certain voltage or so. You might want to be 0.76. You want to know that voltage to that many significant figures. In circuits, oftentimes, if you're 10% off or even 20% off, who cares? Right? Because in these op-amp circuits, it doesn't matter if your gain is 50,000 or 40,000 or 60,000. It just has to be large because there's other elements that are determining the total performance of that circuit. Okay? So when you are designing these things and on exams and that sort, if you're within 10%, as far as I'm concerned, you're right. As long as you did it right, right? You can't just write a number down and then you're right, right? But if you did it right, you're within 10%, you're right. Okay? Finite bandwidth, right? So like we said with the lab, you're going to be designing and building an op-amp that does not have infinite bandwidth, and that's one of the non-idealities of your op-amp. Finite input resistance, right? If the input resistance were smaller, that were not infinite, right, then we'd have to account for current going into the node of this op-amp here. So this op-amp here, we'd have to account for the fact that I minus is not equal to 0, and then the analysis is not as fun, right? We have to do more KCL, KVL to analyze this thing. Finite input capacitance. That's also a problem. That's a capacitance that sometimes you cannot get rid of just through this negative feedback. If this op-amp has its own input capacitance, we're not going to be able to X out this capacitance there. Generates noise. We talked a little bit about noise. We're not going to spend a lot of time on it in this class, but op-amps have noise. They have finite input bias currents if you're doing bipolar op-amps. They have input offset voltages and offset currents. So, in other words, you usually come with this op-amp assuming that these terminals will have the exact same voltage if you apply the same voltage to them. In reality, no, that's not true. It actually is true, but because of the innards of the op-amps, what it really looks like is that even though you apply the same two voltages on these nodes, it looks like one of these voltages is different from the other by a very small amount, and that's what's called an input offset voltage for an op-amp. That actually can screw up a lot of circuits if you don't design them correctly. If you don't bias them correctly, the output can go to infinity, for example, where you want it to be some finite value. Finite slew rate and output swing, these are things we'll talk about later on. And all of the above can be temperature dependent. So not only do they exist there, they change with temperature. Right? An infinite gain doesn't change with temperature because it's infinite, but a finite gain can. And that could be something that affects you if the gain isn't big enough. So a major objective of this class is to understand what gives rise to these non-idealities. Okay, to understand how to design the innards of this thing using transistors, and after understanding that, understand what the non-idealities are. So, one thing I want to do to end up the lecture today is to just take a look at some example circuits that you may see in your everyday usage of electronics. So this is an example actually of a guitar amplifier. This is a solid-state guitar amplifier. And so if any of you guys play any musical instruments, this is a Fender Princeton Chorus. Right? So it basically, look at all the op-amps this thing is using here. right? It's got resistors, it's got op amps, it's got no tubes. So those who care about tube amps, you're not going to like this amplifier. But this is the way these things are designed here, that you've got all these different op amps here, and they're everywhere, right? You see one there, you see one there. In all of these circuits, you've got op amps even together with diodes and that sort of thing here. All of these things, right? You can see op amps are the building blocks of pretty much all electronics. And this is a guitar amplifier, so you can actually pick it up, you can open it up, and you can see the board, and you can identify all the different op amps on that board. Okay, and there's a lot of them being used. But it's not only things that you can see that use these op amps, and I guess this is the innards of an op amp. This is one op amp right here. And this is what you're going to understand how to design by the end of this class. So a few op amps here being used right here just in a differential stage. You've got other op amps here that are level shifting right here. This is an output stage right here. I'm not really explaining this in great detail because you're going to get this by the end of class. Really, by the end of the class, you will know how to design this. And this actually is equal to, whoops, what did I just do? How did I go from that to that? So this actually is equal to one of these. Okay, so each one of these is a number of transistors exactly as is shown here. Okay, and this happens to be the 741 op amp. This has been a workhorse op amp for a long time for a lot of electronics. At least through the 80s and 90s, people use 741s heavily. Today they have some better op amps, some stuff with better noise performance that maybe have JFET inputs and stuff that would be more recommendable to use for audio like this amplifier or so. But op amps are not only used in things where you can look at the circuit board, they're used inside of your cell phones and that sort of thing as well. So this is actually a digital circuit here. Okay, this is a ring oscillator. You could sort of recognize if you've taken 141 or even, does 105 do digital anymore? It used to. It doesn't do any anymore. It's all analog now. Okay. Peaster does 2 days of digital. Okay. Well, 40 may have some digital or so, right? So no? Boy, what's happening? All right. Anyway, this is an inverter here. And you hook up inverters and cascade, you get a ring oscillator there. That's the digital part of this circuit here, actually. This part right here is all analog. So if you look at this, that's an op amp. You may not recognize it there, but right there is an op amp, and I guess arguably I got to include that as well as part of this op amp there. But that op amp is actually part of the most important part of this whole circuit here, because one of the things an oscillator has to do is it has to be able to put out a sinusoid that it's a very specific frequency, very constant frequency. And it turns out this op amp is doing all the work to make sure that the voltage drop across this is not varying with temperature the way that it normally will in any circuit without that op amp. Okay, so you've got an op amp right here. I could show even more circuits here. This is actually a band gap reference. So this is one of the circuits that hopefully you'll be able to analyze by the end of this class. But you can see a lot of structures here. You can't identify anything there. But by the end of this class, you'll just be able to come right out and say, okay, there's my op amp. Right there in that circuit. And you'll be able to just look at this thing and say, okay, here's how that op amp's working. You know, this is actually, they're even showing it here, right? This is one of the terminals of the op amp. There's another terminal of the op amp. So if I had to, right, I could put this here, and I could bring that out as a terminal, bring this out as a terminal. Its output, I guess, is, where is its output? I guess it's here. And that comes out there, right? So that, in that triangular symbol that's an op amp, I've basically specified how this circuit at least shows you your terminals there. Okay? This is what we're learning in this class. And in the next lecture, what you're going to do is go through this material here, which is kind of written material. This is background for you. It's device physics that you probably should know. So device physics and modeling. And that, again, is a lecture that Travis is going to do on Thursday. Okay, so I will see you guys in a while, I guess. Next week on Thursday. Thanks. Yes, all of the notes will go online sometime today or tomorrow.